Okay, students, so welcome. So when we ended up last unit, one of the things that we ended up speaking about was a model for the atom that was called the Bohr model or the planetary model. And the planetary model basically was a view to perceive or see the atom as having a nucleus with a positive charge, but electrons revolving around the nucleus, kind of like the planets orbit around the sun. So not too long thereafter, people began to kind of test this belief and challenge based on some understanding that they had known what would happen with particles that carry a charge. Charged particles that would have curved path motion or circular motion around a region would release energy constantly, continuously as they're circulating around. So scientists began to think, well, this really can't be exactly how this works. So there's a lot of mystery about the idea of the electron, and some of that mystery will get clarified in this unit. Certainly not all of it, but some of it. So like it says here, according to ideas in physics, as the electron would orbit around a nucleus, what should happen is it should continuously lose or release some energy. And that would make it more and more well attracted to the nucleus and have it come spiraling in and crash in on the nucleus. And we know the nucleus has a positive charge. So as a result, people began to think that, wow, we don't really understand too much about this concept of structure for electrons yet. So over the course of time, evidence comes to light, pun intended, light, that there's some correlation between light energy and what atoms can do, specifically the electrons in atoms. So we spoke about this last unit, that the normal position for an electron would be called its ground state. So kind of like right here, this electron's in its ground state. Where it is normally located, it lives there. And what can happen is if that electron absorbs enough energy, it can only jump to whatever the next state is, an excited state, some energy position above its ground state. And it needs to absorb a specific amount of energy. To do that, we would call that specific amount of energy a quantum. So quantum is like the threshold amount of energy that an electron needs to absorb. And what we would notice is the potential for an atom, or at least the electrons in an atom, to release light energy, because that absorbed energy would be released. And as a result, the electron would fall back to its ground state, and we'd end up releasing the same amount of energy that was absorbed, called the quantum. Usually I like to call the released energy photon. It kind of separates energies absorbed, but sometimes released if it caused what we call an excited state, if it caused a quantum leap for an electron. So here we show red light energy striking an electron, and it's not really doing much of anything, right? It's just kind of moving through. So it's not causing that electron to change its energy level position at all. And that's because the light that's coming through is not absorbed, and it doesn't meet the quantum threshold, the minimum amount. So if we change that to maybe kind of an orange light energy, seems like we notice about the same thing. Right? And again, light's not absorbed by the electron. It doesn't meet the quantum threshold, so it stays in the ground state. Finally, we get to green light energy, and all of a sudden the story changes. The electron absorbs that energy. So it does what we call quantum leap. It enters an excited state almost simultaneously, but not exactly simultaneously. It falls back to where it came from, and it releases that energy in an equivalent amount to what it absorbed. And in this case, we witness green visible light come from the atom. And what scientists propose is that every electron has its own position, and to get it to the next excited state, there's a specific quantum, a specific energy amount to get it there. And that can vary from one element to the next for various reasons. One of the reasons is the nucleus has a different number of protons in it, so that attractive force is different. Another reason is the number of rings that we have electrons on varies, right? Every atom, as we progress through the periodic table, has more and more and more electrons in it. So Likewise, if we progressed maybe one more time, so again, our green light energy was absorbed, our green light energy is released as a photon. Now we're going to introduce blue light energy, and something kind of odd in this circumstance, and I'm going to demonstrate this in class when we meet again. So there's an absorption of energy, but it jumps to the position that it had just jumped to when it released green light. So actually what that means is that the light energy that's released from this particular transition, right, that light energy it releases is actually green light. Even though blue light energy caused the electron to change its position, to jump to a higher state, it only needed the quantum that associates to green. So that quantum that associates to green, right, that's the amount of energy needed, or the quantum needed, to get it from the second ring position to the third ring, the excited state. So it'll fall back, right? When it falls back, it releases that light energy. So even though it was blue light energy coming in, green light energy ends up being released. Green light energy is the threshold, the quantum value in this case. So the photon that's released is a little lower in energy than the photon that came in. So well, now, looks like we had a complete computer glitch. So let's see if we can't pick back up where we left off. Let's pause the and it looks like we are back to recording and sharing the information that I wish to. So let's just reactivate that particular setup. So again, our blue light energy coming in, but our green light energy being released, right? That's evidence that there's a minimum amount of energy called the quantum, which is a threshold value. So what might have happened to some of that additional energy? Well, maybe some of it was absorbed as heat energy. Maybe some of it just caused vibration, kinetic energy of the molecules or atoms to move a little faster, but it did not get absorbed by the electron. The electron absorbed what it needed, called the quantum, because it achieved the threshold value, the minimum value. And as a result, it released green light energy, even though it absorbed or it was exposed to blue light energy to begin with. So that's a possibility, and I said I'll demonstrate that the next time that we meet in class. So the energy that gets released is still in the form of green light energy, the photon that's released. Okay, so let's transition forward to something I'd like to explain, and that idea relates to there's a relationship between the different forms of light and some characteristics that they have. We call it wavelength, frequency, and energy. So each of those are related in a very specific way. And I have a nice visual that should help us kind of grasp that idea. So let me just set this up. Okay, and we're going to change this so that it just sends the waves off into space. We're going to turn on an oscillator. Here we go. We want no end. We just send the waves off into space. And we're going to start out by looking at the relationship between frequency and energy of waves. Light travels in waveform. So let's make the frequency as high as we can get it here. So here's our frequency. Frequency actually relates to how many times do we see the wave in some moment of time, usually like a second. So the unit for frequency is hertz, which relates to that, wave cycles per second. So if we pause this guy, we can count from top to bottom sort of how many waves we see. So we paused it, and what we're going to do is we're going to count from top to bottom. I'm sorry, top to top. 1 wave, 2 waves, 3 waves. So we see 3 waves, frequency 3. When we see 3 waves, there's a certain amount of energy being transferred. So the energy is being transferred through the rope or the string at a frequency of 3. So let's take that frequency and reduce it down to 1. Now we should only be seeing about 1 wave. Let's pause it and let's kind of show you what I mean by 1 wave. generally from top to top or bottom to bottom. So here is generally the top, here is generally the top, right? So there's one wave passing by when the frequency is 1 in this unit of time. So we notice that the oscillator's not moving as rapidly up and down, and it's making waveforms that are less frequent. So less frequent waves are lower energy. Low frequency, low energy. Let's bump up the frequency. Frequency 2. All right, frequency 2. What we're going to notice are 2 waveforms then. So let's just kind of highlight them. Let's go bottom to bottom this time. 1. And right over here, right around where the green one would be 2. So now we see 2 waves, right? The frequency is now higher than it was when it was at 1. So now there's a little more energy moving through the rope than there was when there was a frequency of 1. So let's decrease the frequency again and watch what happens to the energy amount, right? The oscillator's not providing as much energy as we lower the frequency, right? The oscillator, as we add more energy to the rope or string, it moves faster up and down and it transfers more energy. So more frequent, more energy. Less frequent, less energy. Okay, let's take a look at what we call wavelength. So wavelength is like from bottom to bottom or top to top, how long a wave is. So let's mark up when the frequency is 3 in pink. So bottom to bottom, bottom to bottom, bottom to bottom. So there's a wavelength right there. There's a wavelength right there. And another wavelength right there. 3 identical wavelengths when the frequency is 3. It's not a coincidence that there's 3 waves. Frequency is 3. So our wavelength looks this way. So when it's pink, right, our frequency is 3 hertz, 3 Hz. Let's change the frequency down to 2. And watch what happens to the wavelength. Frequency 2. All right, let's pause it there. So now wavelength, let's measure from bottom to bottom this time. So let's use a different color. Now we'll use our black. From bottom to bottom, right chia to right chia, right? And then right chia. So now look what happened, right? We just made the frequency lower and it made the waves longer. Long waves, low frequency, right? So the frequency and the wavelength are sort of opposite to one another. When the frequency gets lower, the waves get longer. Let's change it down to 1. So frequency of 1. And there we go, close enough. I guess we could get it exact there for those of you that like a level of exact. Okay, frequency of 1, we'll pause it. And let's go I guess bottom. Let's go top to top. So top to top, we'll mark that. We'll use blue, right? So we'll kind of call this the top right here, and where it reaches its peak is probably right about here. Notice what happened, right? Most of the screen is one waveform now. So that's because now we have a really long wave because it's low frequency. Low frequency, long waves, high frequency, short waves. So this lets you visualize that. That's the purpose of this particular animation for us. Okay. So what we notice is there's a relationship between all of the things that move at the speed of light. We call those the electromagnetic spectrum. And I like to say it's ERMIVIXCA. So ERMIVIXCA is an acronym, and it stands for radio waves, microwave, infrared, visible, ultraviolet, X-ray, gamma ray. And ERMIVIXCA is in order from longest waves to shortest waves. Our longest waves are our radio waves. Our shortest waves would be our gamma rays. It's also in order from lowest energy to highest energy. Our lowest energy would be radio waves. Our highest energy would be gamma rays, right? It's also in frequency. Our lowest frequency would be radio waves. Our highest frequency would be gamma rays. Interestingly enough, what fits in here where the V is, right? V stands for visible light. Visible light can be broken down into different components: red, orange, yellow, green, blue, indigo, violet. So notice that red is closer to the low or the long end of the scale, yet violet is a little closer to the short end of the scale. Red light is longer waves, lower energy, lower frequency. Violet light is shorter waves, right? Higher energy, higher frequency when we compare it back to red. So Ermivixka, radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, gamma rays. Okay, same sort of visual right here, right? Just a little additional information on here. But this one shows kind of over on the left, it shows long waves, right? Very long waves correlate with low frequency and low energy. So our long waves are radio waves, our microwaves, right? Our short waves are X-rays, or gamma rays, and our in-between Ermivixka. Again, Roy G. Biv fits in where visible light would be. Hey, look at this, no coincidence. Pretty cool thing. Infrared, red bumps right up against that. Ultraviolet, violet bumps right up against that. That's not a coincidence. So they're very close in wavelength. Infrared is right along the scale for red, visible light. Ultraviolet is right to the right of violet on the visible spectrum. So what we're going to come to look at in a moment is this fact at the top of the paper, is that all of these travel at the same speed. It's called the speed of light. In a vacuum, that would be 3 × 10⁸ meters per second. So they're all considered light forms because they all travel with the same characteristic speed that any form of electromagnetic radiation would. So radio waves, microwave, infrared, visible, ultraviolet, X-ray, gamma ray, Ermivixka. So if we were going to compare just maybe some colored light, so let's say we wanted to compare red, green, and blue light. And I wanted to know which of these had lowest energy. What I'd look for is I'd look on Ermivixka, right? I'd look on the scale for Ermivixka. Does red, green, or blue have lowest energy? Well, red, green, or blue. So red is furthest to the left, right? So red would be the lowest energy form, right? So red would be our lowest form of energy out of red, green, or blue. Okay, we could do the same thing for frequency or wavelength, right? Long waves versus short waves. So if I wanted to compare long and short waves, there's a simple way to do that. Okay, so let's say we wanted to compare ultraviolet light, X-ray, and microwave, and we want to know which of these are the longest waves. So we just look at Ermivixka. Ultraviolet's here, right? X-ray is here, microwave is over here. So microwave, because it's closer to where long is on this scale, it ranges from short back to long on the left side. It makes sense. Long is on the left. Low energy is on the left as well. So microwave would be our longest waveform of those three. It would also be our lowest energy and lowest frequency. Counter to that, if we want to look at what would be the shortest wave of these, then we'd look at what's furthest to the right, and then we would say X-rays. X-rays would be our shortest waves, which means they would be our highest frequency and our highest energy, at least out of those three choices. So that's what I would like you to be able to do, compare the different forms of electromagnetic radiation. I like to call them Ermivixka. Easy way to remember it. Okay, so let's transition forward to an interesting aspect of what people were able to observe. So through observation, a gentleman by the name of Einstein proposed that there's something really interesting that happens if we kind of observe how different metals interact with light energy. And this comes to be known as the photoelectric effect. So I want to kind of play this segment of video for you and kind of stop it and highlight it for a few key points in the lesson. But there we go.
The photoelectric effect. The photoelectric effect was a very important discovery that was made in the early 1900s and was first correctly interpreted by Albert Einstein. The photoelectric effect shows us that when light strikes a metal surface, electrons are ejected from that metal surface.
Now, it doesn't always show us that. It only shows us that if it's the right kind of light. So right now, I'm going to annotate a little bit here, right? I don't think that spotlight works on my computer for some reason. So right now it says that it's set.
The first important thing you need to know is that the brighter the light, the greater the current. That is, the greater the number of electrons that are ejected from the metal. So a brighter light creates a larger current, which means more electrons ejected from the metal. Photoelectric, it's a linear relationship. Photoelectric is very important. So no matter how low the intensity is, at zero, first correctly, you'll still have some electrons being ejected from the photoelectric. Okay, the second thing that you need to know.
All right, let's pause this for just a moment. Okay, my apologies. We're fighting the network here still a little bit today, but I think we may be overcoming that because students are being dismissed now. So we're looking at this thing called the photoelectric effect.
It shows us that when light strikes a metal surface, electrons are ejected from that metal surface. The first important thing you need to know is that the brighter the light, the greater the current.
So what he's explaining here is what's going on is the little electrons moving across here, that's representative of current flow, the little purple dots. They're striking light on this metal plate, and it looks like if you read right here on the little scale, it says it's kind of equivalent to UV light. UV light's fairly energetic light. So whatever metal plate this is, it says it happens to be calcium, is emitting its electrons. As the light strikes the calcium, it causes electrons to be released, and we call that the photoelectric effect. So it's because the light striking the metal plate is causing. This is kind of like the precursor to solar cells, how a solar cell can generate electricity. So Einstein's credited for kind of observing this and creating some meaning for it.
That is, the greater the number of electrons that are ejected from the metal. So a brighter light creates a larger current, which means more electrons ejected from the metal. You'll notice it's a linear relationship that goes through zero. So no matter how low the intensity is, as long as you're not at zero, you'll still have some electrons being ejected from the metal.
And what he didn't say is that magic word quantum. So the quantum that allows the electrons to be ejected is something equivalent to visible light. And right here is the wavelength, 218 nanometers. So that's how long the waveform is. It's very, very, very short. Okay.
Okay, the second thing that you need to know is that these electrons that are ejected from the metal have a certain amount of energy. That energy was determined by using a voltage source to try and stop the electrons. So we make one of these plates negative, and it starts repelling the electrons away from it. And when we hit just the right voltage, we'll get it so that none of these electrons can make it across to the other plate. At that point, the current will drop down to zero.
And when the current drops down to zero, now we know how much energy those electrons were needed. We know the quantum value needed to eject the electrons. And what Einstein investigates further is changing the different metal plates to different types of metals, changing the range of light energy used, and is able to draw similar conclusions in each case. Let's let it play a little bit more.
Once we have the current down at 0, we can find the energy of these electrons by using the formula. Voltage, that's the voltage of our voltage source, is equal to the kinetic energy of the electrons, which will go from the formula voltage equals work over charge. Again, the work is the kinetic energy of electrons, the Q is the charge of the electron, and V is the voltage required to stop the electrons. We know we stop the electrons when the current gets down to 0. Okay, so we now know that brighter light knocks off more electrons. We now know the energy of the electrons, and we know that energy is determined by the voltage required to stop them. We now want to see, is there any relationship between the energy of electrons and the light that we're shining onto the surface? So if you notice this graph, as we increase the frequency of the light by decreasing the wavelength, you'll notice that the energy of electrons increases. Similarly, when we lower the frequency of the light, the energy of the electron decreases until eventually you hit a point.
Notice now it's a light that you can see, kind of violet colored light. He slid the slider over to like the purple region. So now we're in the violet region, and it stops ejecting electrons, evidence that the quantum threshold has not been achieved. So with the metal calcium, the quantum threshold is going to be different than other metals. So that's kind of what Einstein proposed with what the photoelectric effect actually means.
Where no more electrons are ejected from the metal. At that point, you have been said to cross the threshold frequency or the threshold wavelength for that material. From that point,
so you know he could go into the blue, the green, the yellow, the orange, or the red region, and we're actually just getting lower in energy. So there's no way those are going to eject electrons. So there's a threshold for every metal element required. It's called the photoelectric effect.
Going on, no more electrons will be ejected from the metal.
So you can make that light as intense as you want, the brightest red laser you could ever get. It's still not going to eject because red light energy is not energetic enough. It doesn't carry the right frequency or wavelength.
Each type of metal will have its own threshold. So the first metal we did was calcium. We're now going to look at it for sodium.
So there will be a point where sodium will begin to eject electrons.
And you'll notice that it has a lower threshold frequency.
And that's really right around the area or the region of purple or violet light, kind of right in between violet and ultraviolet. So it's kind of close to where the first one was called calcium, but it ejects electrons a little bit easier than calcium does because it does so at a lower energy form of light. Okay, so that's in a nutshell what we mean by the photoelectric effect. Okay, so what does Einstein propose? That when we shine light on a surface, it can absorb energy. The electrons in there can be ejected if they're energetic enough, if it meets the threshold value that we like to call a quantum. And he proposes that the electrons in all metal atoms have a very specific amount needed. So if it were calcium versus lithium versus copper, that threshold would be different. So if we don't achieve that threshold, then no energy, no electricity, no current would flow. And he sort of demonstrated that light sort of behaves like particles. It doesn't just move in waveform. Light intensity can cause more current flow. So as we strike a metal surface with more intense light, the same the same energy amount, but kind of more waves of the same energy, we get more current flow to be released. So it's kind of like the intensity of light is similar to its mass. So the photons that meet the threshold value kind of have, they sort of represent a greater mass. What I mean by that is we can release more photons because there's more waves of the same energy of light striking an atom. And that's kind of like having particle-like behavior. And there was a real debate going on about whether light was what we would call waveform only or a particle form only, or it had duality. It behaved as both particle and wave. And that's kind of what our current belief is, without getting too into the gory detail. So in around the same time, some other evidence about the idea of quantum from a gentleman by the name of Max Planck proposed through some observation what happens when you observe objects that heat up as their temperature varies. As it gets hotter and hotter and hotter, we tend to see different colors of glow. So for instance, we turn on the burner in the oven, the first color we would see would kind of be a reddish. As we let it get hotter and hotter and hotter, it would turn orange. If it could do so without melting, it would probably turn like this yellowish color, maybe a green next, then a blue. Obviously, it probably would have melted long before that happened. And what he confirms is almost the same thing that Einstein confirms. Hey, these colors suggest there's an energy threshold. There's a quantum value we need to achieve for it to glow a very specific color. And if we don't achieve that quantum, it won't glow that color. And he really is responsible for developing the mathematical equation that takes energy and relates it directly to the frequency of the form of light that we're talking about. So the value that relates them together was called Planck's constant, 6.626 joules per second. So the frequency of light is directly related to the energy that it possesses. Okay, so we wrap up with really this last concept. This last concept is a way to relate the frequency of any form of light to its wavelength. So it's always related through the speed of light. The speed of light is a constant. In this formula, it's c. So we'll always use 3 × 10⁸ meters per second for c. So we're either going to substitute in for a frequency, which is the Greek letter lambda, or we're going to, wavelength, Greek letter lambda, or we're going to substitute in for a frequency, Greek letter nu. Lambda times nu is always equal to the speed of light. So in this first example, we're going to substitute in the speed of light. It says the blue color of the sky is the result of scattering of sunlight. The blue light has a frequency of 7.5 × 10⁻14 hertz. Calculate the wavelength in meters. So speed of light, c, is equal to lambda nu. Remember, lambda means frequency. Nu means, excuse me, I said that wrong again. Lambda means wavelength. Frequency means hertz. So wavelength is in meters. Frequency is in hertz. So our nu is our frequency. Our lambda is our wavelength. All right, let's plug in. So 3 × 10⁸ is our speed of light. That's our c. We just plugged in for that. In the words, they give us the frequency. What they don't give us is the wavelength. So we're going to leave lambda alone like it's a variable, almost like it's x. Then we're going to plug in, right, 7.5 × 10⁻14. And what we're going to do is we're going to solve for lambda. Right? When we solve for lambda, well, to isolate lambda, what we're going to do is we're going to divide each side by the same factor to isolate lambda to make certain that lambda is by itself. So let's just change the pen color here to maybe a blue. So we want to get lambda by itself. So on the right side, we'll divide by 7.5 × 10⁻14. If we do it to the right side, we got to do it to the left side. Divide by 7.5 × 10⁻14. And what that's going to do is these will cancel and it will leave lambda isolated by itself on the right side. And then in the calculator, we're going to take 3 times 10 to the 8th, right? In scientific notation, 3 times 10 to the 8th power, not 3 to the 8th power, 3 times 10 to the 8th power. We're going to divide that by 7.5 times 10 to the 14th power. And we're going to get an answer of 4 times 10 to the, let's see, what is that? 3, 6, 7. 4 times 10 to the minus 7. And we just solve for what we call wavelength. Wavelength would be in meters. So 4 times 10 to the minus 7 meters would be the wavelength of light that has a frequency of 7.5 times 10 to the 14 hertz, blue color light. If we look at the second example here, now it asks us to solve for frequency. Well, remember, frequency is nu in the formula, the thing that looks like a V. We do the same thing though, C equals lambda nu, right? So C is always 3 times 10 to the 8th power, speed of light. Right? And speed of light is always equal to lambda nu. In this case, they give us lambda. They give us the wavelength, 6.25 times 10 to the minus 9. What they don't give us is nu, that funny looking V, right? So we want to isolate or solve for nu in this case. So to isolate or solve for nu, right, what we'll do is we will divide each side by 6.25 times 10 to the minus 9. And that's going to isolate nu, right? That's going to cancel these guys. And we'll just do our division in our calculator, right? 3 times 10 to the 8th power divided by 6.25 times 10 to the minus 9 power. So let's just double check. 3 times 10 to the 8th divided by 6.25 times 10 to the minus 9. And we get a value for nu of 4.8 times 10 to the 16th power. So 4.8 times 10 to the 16th. And that is now a frequency, and the unit for frequency, like it says up here, is hertz. So 4.8 times 10 to the 16 hertz. You just want to be careful. Some of you like to use this caret key as an exponent. So let me just demonstrate if you're going to be doing that. So if you enter in your calculator 3.8 times 10, and then you use your caret key, caret 8, you're going to want to make certain that you put that in parentheses before you start. Otherwise, it's going to make what we call an order of operations error. Likewise, when you go to do the bottom, do the same thing. 6.25 times 10. If you like to use that caret key on your calculator for an exponent, which some of you do, I know, you're going to want to wrap that in parentheses. And you're going to get the same answer that we just got right here. So that concludes the introduction to our first lesson on what we call the quantum mechanical model. More importantly, that relationship between frequency, energy, and wavelength, and how that relates to the concept called the quantum, the minimum amount of energy needed to cause an excited electron, or the threshold, as some people like to say. So until the next time, I bid you well. I'll talk to you again soon, folks.